So in antennas, just we are giving the input signal as a RF source that was converted into the electromagnetic waves. That's why simply here so many different techniques are there. By using the HFSS software, we design the antennas. So initially that is the common technique is microstrip feed line. So what is meant by microstrip patch antenna? Anyone have the idea? Hello? Both. Is it required to share the? Is it required to share the both links or single link? Okay. Okay. I will share. Are you visible my screen? Okay. So this is the microstrip patch antenna. That means see here, this is the green line is a complete substrate.
Sir, we can't see anything.
Yes, sir. Screen is not visible.
Everyone getting or not? Link 1 or
no,
link
sir.
2?
Link 1, sir.
Link 1, sir.
Link 1 also. Wait. Right now getting?
No, sir, it's not sharing yet.
Okay, wait. Not possible to share the screen in 2 links. Right now it is visible for
yes,
all.
Sir. Yes, sir.
Yes, sir.
Okay. So this is the simple geometry of the microstrip patch antenna. That means microstrip patch antenna consists of a radiating patch. That means this is the patch antenna is there. So this entire green is the substrate and above is the patch, that is nothing but a radiating element on one side of the dielectric substrate, which has the another ground plane is there. This is the ground plane. So this is the ground, this is the radiating patch, this is the substrate. So that's why the antenna, what is the definition? It converts it likes as a transducer. That means it converts RF signal into electromagnetic waves. So this is the radiating patch. That's why we are giving the source into the patch that radiates the electromagnetic waves into the free space. That's why, so we design any antenna, it requires the substrate and a radiating patch along with the ground. So simply microstrip patch consists of a radiating patch on one side of the dielectric substrate, which has the another side as a ground plane. So this is simply microstrip patch antenna. That's why we go for the design of microstrip patch antenna by using HFSS software. So everyone using HFSS or which version? 2014 or 2015? Okay, I am using the 2018 version. Maybe little bit changes are there. Don't confuse.
Sir, we are using 15, sir.
Okay. What are the experiments already performed in antenna in the 4th sem? Hello? No one is responding.
Sir, building of just normal patch antennas.
Only patch antennas, na?
Yes, sir.
Any another feeding techniques? Okay. So today I'm just explain the simple microstrip patch antenna. That's why just remind how to design microstrip patch antenna. Then later we go for the microwave device circuits. So this is the HFSS screen. This is the project manager. So this is the what you design on the project. This is the projects here. So this is the message manager. So initially we design the first what we taking microstrip patch antenna consists of a patch, substrate and ground. So that's why initially we are taking the substrate. So that is a 3-dimensional. That's why go for the, you have idea about all this. That's why I'm directly discussing. Any more? That's why I will explain each by each. Tell me first. So this is the rotation. Just what you the coordinations rotation. So generally is a 3D. That's why this is the x-axis. So this is the y-axis. This is the z-axis. So initially I am taking the substrate. That's why this is the go for the menu box. Here showing the radiation box or simply 3-dimensional box. So this is the radiation box. Click on that radiation box. You click on any place. So this is the 3D box. So go to the click on box here. See here. The name is box 1. This is the material is vacuum. That's why here so many materials are there. That is the substrates. Click on this. Go to the edit. So these are the different substrates. Different substrate materials are there. So generally we are preferring the FR4. That's why we are preferring the FR4 substrate means the FR4 the cost is very cheap and easily available in the market. So another substrates, the cost is high and did not available in the market. That's why simply taking the FR4, we are getting, if you search in this line, search in the box, you are getting the FR4 epoxy. So click on the FR4 epoxy. Okay. So here appear the FR4 substrate. You can choose any color for this one. So just I am choosing as a, this is the color of the substrate. Just we are selecting the substrate, did not assign the values. So I am taking the substrate length and width. We have already know the formulas. So mathematical formulas are there. Okay, we have already studied in the antenna design. So what is the patch length? What is the feed length? So based on that values, you can calculate the substrate length, width, patch dimensions, everything. So I'm choosing the so click on the radiation box. So go to the create box. Here some position is there, position, X value, Y value, Z value. So we are taking the substrate as a 3D. That's why is it required to take the X value in X direction, Y value and Z value. So for the substrate, so initially I'm taking -8.61, 7.39. So this is the X value position. This is the Y value. -8.61 is the X value, 7.39 a Y value, 0 is the Z value. Here this is the X. I am taking the X value length as so 17.22 and Y value -14.78. So substrate height is 1.6. Is it clear? Anyone have doubts? So this is the simply first initially we are taking the substrate dimensions. So that's why I'm change the name as substrate. So this is the substrate. So length is 17.22, width is 14.78. So height of the substrate is 1.6. This is the substrate value. Then what you required, another one is so this is the first selecting the substrate, then patch. Patch is nothing but a radiating element. In the below is ground is there. So that's why then I'm designing the patch dimensions. So patch is the 2D dimensional. That's why we are taking the only X and Y values. For the 3D dimensionals, go for the box. For the 2D dimensions here, so many shapes are there. This is the rectangular shape, this is the ellipse shape, this is the circle shape, this is the octagon shape. So generally for the 2-dimensional, you go for the rectangular box. So this is the rectangular placed on the substrate on any place. So this color is nothing but a patch, but you can choose the patch dimensions also. So that's why click on this here. When we choosing the 2D element, is automatically coming into the project menu. So this is the rectangular one. So go click on this rectangular one. So assign the name as patch and change the color. So give the dimensions of the patch dimensions. So previous we are giving the substrate dimensions. Right now I am giving the patch dimensions. So the patch dimensions are, I'm choosing minus 3.91 minus 4.41 0.6. So x value is 7.62. Y value is 5.18. So this is the patch dimensions. Is it clear? This pink is the patch. This is the substrate. So to design any microstrip patch antenna, it requires the three. One is the radiate element, that is the patch. So this is the substrate. Another one is the ground. So you can assign the ground. So just rotate this one. So this is the below. So this is the above. So below we are placing the ground. That's why simply rotating at the back side, back view. So place the rectangular within the same dimensions. So change the name. This is ground. You can change the color also. So to design the microstrip patch antenna, so it requires, first one is this color is substrate, this is the patch, so this is the red is the ground. Then we are giving to the feeding. That means simply antenna definition is, antenna means it acts as a transducer, that means transmitting purpose and receiving purpose. So suppose we are giving the source, that is the excitation. Excitation means just we are giving the input signal. So input signal to this patch, the radiations and electromagnetic waves produced by these patch element. That's why for this design it requires the input source. So this is input source is connected in between patch as well as the ground. Understood? So that's why, see here, so this is the x-axis. So this green is the y-axis. So this is the z-axis. We are giving the input signal that is covered by below ground plane and above patch or radiating element. That's why just we are giving the input source in between these two. What is the dimensions of here? Which dimension we are choosing as the input source? Understood or not? No one is responding. Hello?
Yes, sir.
Not visible.
Yes, sir.
Visible or not? Both links.
Visible, sir. Visible.
Visible, sir.
Okay. First link is maximum reached. That's why the screen share is not possible to share both the links. That's the problem.
Sir, it should be able to share means both the links.
Wait. So who joined the full members now? 101 members. That link is visible now.
Yes, sir.
The second one is not visible. That's why. Now both is okay.
Yes, sir.
Okay. So to design the microstrip patch antenna, so it requires the substrate. This is the substrate. So this is the patch and this is the ground. So we are giving the excitation for the radiating element, that is the patch. It converts the RF signals into the EM waves. That's why we are applying the feeding or excitation in between these two elements. That means it covers the ground plane as well as radiating phase. That means this is the top, this is the bottom. That's why simply we are connecting the in between these two. So in between these two means simply this is the x-axis. So this is the x-axis, this is the y-axis, this is the z-axis. We are connecting the excitation or feed in between the xz directions. That's why the input source is touched to the top plane as well as ground plane. That's why we are choosing the excitation in xz plane. So for the connection, just we am connecting the one rectangular to the patch. So that's why this is the radiating patch, or simply this is the patch. This is the feeding element. Okay, wait, change the feeding element. This is the feed. Feed dimensions are 275. So just this is the patch. That's why for the connecting purpose, I am taking the some length that is connected to the patch. So this is the simply called as a feed. So we are connecting the excitation between the top layer and the bottom layer. So that's why we are choosing the dimensions or coordinates. Simply go to this. Actually previous is the XY coordinate is there. So change the XY to Z axis. So connecting the so this is the excitation or RF signal source. That's why simply give the name as port excitation. This is the port. Can you give the color? Okay, any doubts is there? Simply microstrip patch and dimension consists of the radiating patch. This is the radiating patch. So this is the ground plane. This is the substrate. Is it clear? Anyone having doubts still now for this design? So design part is completed. Just we are giving the excitation.
Guys, if you're facing any problem, then ask some question according to your problem. Okay. So Anand sir will discuss about this thing. Okay.
Yeah,
Problem.
they did not respond. No one. Raju, no one is responding. No one asking the questions.
ओके ओके आनंद बाबू ओके तो गाइस आप लोगों को समझ में आ रहा है ना सब कुछ
Yes, sir.
Yes, sir.
श्योर ना क्योंकि ये एग्जाम भी रहेगा या ठीक है इस बार प्रैक्टिकल पे होगा सो गाइस लिसन केयरफुली दिस थिंग्स एंड इफ यू हैव एनी प्रॉब्लम एनी डाउट आप लोग बता सकते हैं ठीक है आनंद सर इज देयर सो ही विल एक्सप्लेन
सर एक्चुअली लास्ट सेमेस्टर हमें थोड़ा इजी मतलब पूरा क्लासेस नहीं मिला था इसका लैब
अच्छा
HMSS का
Yes, yes. In the fourth semester,
so clear these things in between your semester okay swell
ओके सर
इस बार आप क्लियर कर लो कोई भी डाउट रहेगा तो क्लियर कर लो सर इज देयर ओके सो नो प्रॉब्लम डोंट वरी
ओके सर
okay, that's why here designing part is completed. That means taking the substrate, that is the FR4 epoxy. The height of the substrate is 1.6. So designing the patch on top of the substrate. So below is also full ground. So to connect the connectivity between the patch and the ground, I am giving the source that is nothing but a simply excitation that is in between the Z X coordinates. So it covers both the top plane and the bottom plane. So then we are giving the excitation here. Just so click this one and right click, go to the see here. So many options are there. Select this one and right click, go to the assign excitation. So assign excitation is here, wave port or lumped port or flow port. So many ports are there. So we are giving to the lumped port. So in the lumped port, so that means input matching is required. That means whatever the radiating patch and input source, it requires the 50 ohms impedance matching. That's why that is automatically came into the software. So by that is by default designing 50 ohms. That's why clicking on next. So one window is open. So in that window, none is there. Here clicking on this, go to the new line, select the new line. So this new line is placed from bottom to top. Click this one. We are getting the defined. If getting the defined, that the connection is okay. Otherwise, you did not getting the defined option, that is your excitation is wrong. That means input source is wrong. Here getting the defined, that's why go to the next step. So finally 50 ohms is coming. So this is the finishing. That means just we are giving the input source for this patch. So generally, see here. So this is the simulation part only. For practically, in the antennas means in the above, for the current flowing, it is required the copper plate, and below means the ground is also generally, that is the copper plates are there. But in the simulation, we are using simply radiating patch and ground. That's why we did not give the current flowing. That means this is not the conducting materials. So these, that means this is the radiating patching. These are simply patch. This patch and this patch becomes as a conducting plane. We are giving the perfect electric. That's why just clicking on these two, whatever the patch value is there. So this is the patch. This is the patch. So this is the ground. So put the control and select the patch and ground. Click on right click. So here assign boundary is there. Previous is the assign excitation. Here this is the assign boundary. In the assign boundary, go to the perfect E. That means a perfect electric. That means it acts as a conducting plane. So click on this. So see here in the boundaries. So this is the so I'm at a time giving the both. You can use separately, no problem. So I'm deleting this one, giving separately. That means so first to select the patch, then go to the right click, assign boundary, perfect E. So this is the perfect E for patch. So similarly, select the, see here, we are not assigning the perfect E. This is the unassigned. That means simply undefined. So if you previously see the here, if we are giving the electric field for the patch, so here this one, then we are the simulation. So tool means here. So this the that's the what you require first patch patterns and the boundaries. This all these are the three steps. First state, patch, boundaries and excitation. Then go for the missions. So mission operations means go to HSS. Yeah. So in right side here, MS spot is there, and similarly we choose the go to the HFSS. HFSS. Here is setup. So you can directly click on this analysis spot, or otherwise in the menu bar. This is the menu bar. Here file, edit, view, project, draw modeler, HFSS. In the menu bar, click on the HFSS. Go to the analysis setup. The analysis setup is showing the add solution setup. So click on this. So this is whatever the frequency you design some antenna, that antenna is radiating or resonates at particular frequency. That's why. So by default you can give any frequency, that means either 5 or 10 or 12, whatever it may be. That's why I'm choosing simply for 5 gigahertz. This is the maximum number of passes. Means if you are taking the for the graph purpose, we are taking the number of passes. So this is the variation between the scale. That's why 0.02. So click on this. Here go to the analysis. Your setup is getting setup 1. This is already assigned. Click on once again. Click on this one. So go to the add frequency. Add frequency sweep. So this frequency sweep means, so your antenna showing in between the frequency ranges. Suppose here by default getting 1 gigahertz, 10 gigahertz. So I am choosing 1 gigahertz to 15 gigahertz. So in this frequency range, my antenna is operating. Is it clear? So here design part is completed. After designing, we are giving the boundaries and excitation. Boundaries means whatever you design, that design was converted into the copper plates for the current flowing purpose. That means we are giving the input source. So first design part, then boundaries and excitations, then mesh operations. Now mesh operations are completed and analysis setup also completed. So then go for the finally is the radiation box is required for this antenna design. So for the why we are choosing the radiation box means in environment so many effects are there, ohmic losses or radiation effects or fringing fields. So to avoid these all effects, we are choosing the radiation box. So here radiation box, two options are there. You can choose by default, you can choose the radiation box. So in 15 version, you are using the 15 version. In the 15 version, I think that option is available or not, I don't know. But this is the latest version. If you go to the HFSS, here HFSS is there. Then go to model in create open region. This is creates the radiation box for our corresponding values. So this is the radiation box. Or otherwise, you can remove the radiation box. So I am removing the radiation box. So I think previously we are giving the manually. So choose the 3D modeler box. Sorry, it did not change the dimensions. So XYZ. Choose the 3D radiator box. This is the 3D box. So this is the radiation. Click on this radiation box. So this radiation box is filled with vacuum or air. That's why here already vacuum is there. So continuing with vacuum and choose the some visibility color. And change the dimensions. Listen, previously actually we designed the patch. That means along with the substrate. Substrate height is 1.6. On the 1.6 above we are placing the patch. In below is the ground are there. Here we are choosing the radiation boxes is the formula is lambda by 4. Lambda is the first resonating frequency. So you are suppose for the design means initially we are choosing the applications and whatever the frequency. Suppose so I am choosing around 10 gigahertz. So based on the 10 gigahertz means you know the resonating frequency. F is the 10 gigahertz corresponding the frequency. You find out the wavelength. That wavelength is you are getting based on the your resonating frequencies. So here the radiation box is generally choosing as lambda by 4. So that's why based on that calculations I am choosing the radiation box is the position values is minus 12 or 10 minus 4. So this is the x value is double 24, y value is also double, that is 20. Z is choosing the 12 minus 4. So this is the radiation box. Okay, any more doubts still now? So simply listen, first to design the, take the substrate and design the patch on above the substrate, and below the substrate we are connecting the ground plane. That's why a design part is completed. That is simple antenna. Then give the excitation. Excitation means we are giving the input source to your design structure. We did not give the input source, the antenna did not resonating or radiating. So that's why we are giving the excitation. So that excitation covers the attached with the both the top plane and bottom plane. That's why I'm choosing the XZ plane. I am giving the excitation. Then so these designs converted into the copper. That's why we are giving the perfect electric conducting materials. That is PEF, perfect E1 and perfect E2. That is perfect E1 means this is the patch on top of the substrate. PE2 means below of the patch. So then another step is mesh operations. Mesh operations means directly here in the project manager it's showing the analysis. So click on that analysis, or otherwise go to the menu bar. In the menu HFSS is there. On that HFSS go to the analysis setup, add the solution frequency. Add the solution frequency means so at whatever frequency your antenna is resonating. I am choosing the 5 gigahertz. Okay, but you can choose 10 gigahertz. You can give the 10 gigahertz as a solution frequency. So that is the analysis setup. Then finally give the radiation box. These are the steps followed in the HFSS software. So then everything is completed. Go for the checking. That means go to HFSS. Your validation check is there. So this is the validation check. Click on this. So here validation check, this is the design settings is completed, 3D model, boundaries and excitations, and the mesh operations also completed, analysis setup, optometrics and radiation, everything is completed. If you did not completing any one, here did not showing the green mark, it show the red mark, that is the cross. So to rectify that one. So everything is completed, then go to the run. So go to the HFSS, analyze all, So for this, I did not save. Go to the soft. Take some time to run this design. In previous fourth semester, you learn only microstrip feeding or any other feedings are learned. Hello, these students.
Only microstrip feeding, sir.
Only microstrip
Microstrip
feeding.
only.
Only microstrip feeding or CPW feeding or coax feeding. Or learn only this one, na?
Yes, sir. Sir, there were less number of classes.
Acha, okay.
So only 3 experiments were done.
Okay, up to now, any doubts are there in this design? You know, the already theory concept is there. That's why that antenna theory already studied in previous classes. That is applicable to the practical here, but using the software, HFSS software. So then these are already studied in the antenna. Then go for the microwave devices. What are the microwave frequencies? Subject taught or not? Hello? Are you there in the class or are absenting? Just connected in the online and everyone doing their own works. No one is responding, no one give the answer. What are the frequency ranges? Microwave frequency ranges? Already studied in the analog communications, I think. Analog communications is completed or not? So,
Yes, sir.
okay, listen. So you are not responding anyone. So for the next classes, I am randomly pick up the roll numbers. Okay, I am asked the questions. So regarding the subject, that means just to asking the basic fundamentals. That is not required to study. Already completed. So no one is responding based on my questions. That's why I am randomly pick your roll numbers. Asking the questions. Who did not say the answers, I will put the assignment 0 marks and attendance also 0 for this lab. Why we are stabling? Already you in the third year. You know the all fundamentals. You are the easy students. You don't know about the frequency ranges and electronics part is completed. Then we are coming into the communication part. Your students are the communication students, but you did not communicate to the faculty. What I am asking the questions, you did not responding. How can I understood? So see here, this is the message window here, and finally getting the normal completion of simulation on server. This is the complete the simulation. If you go for the checking the results, so here it already is there. The left side, that is the project manager results are there. Click on the right side here, showing the so many windows, that is the create model solution data report. So go to the rectangular plot. Here in the rectangular plot, you studied already so many antenna parameters in your theory. That is VSWR, gain, radiation pattern, main lobe, major lobe, front to back ratio, Y parameters, Z parameters. You already so many antenna parameters, antenna fundamentals are studied. So initially, if you design any antenna, you check the reflection coefficient. That means that is the S parameters. So you are giving the input source, that based on the input source, how much is reflected back. That means here suppose you design an antenna, we are giving the excitation, that is the RF input signal. That means radio frequency input signal we are giving to the antenna. So how much is radiated? So we did not find out the how much radiated into the field. That is we can't find. So we find the whatever the input we are giving, that that means already we are giving the 50 ohms impedance already previously shown in the excitation. So that's why here you are checking the reflection coefficient. That means S parameters. S parameters means S11. That is the scattering parameters. In the scattering parameters, S11, S12, so many ports are there. Suppose in this design I am using the only single port. That's why I am checking the S11. That is the reflection coefficient. So reflection coefficient, how much reflected? That means the reflection is less. You are giving the input source is maximum transfer into the free space. Yes, understood this point or not? So for that one, we are checking the S parameter. S11 is very less value. So here, this is the S parameter, S11 dB. So generate new report here. So see here. So generally S parameter showing minus 10 dB level. So minus 10 dB means here you are getting the 3 resonating frequencies. This is the resonating frequency 1. This is the resonating frequency 2. This is the resonating frequency 3. So select this one. This means this antenna produce the multi-band applications. So here, see one. So first resonating frequency is 12.66. The reflection coefficient is minus 21. 13.7. That is the reflection coefficient is minus 26.5. So third one is the 14.72 minus 27.18. What is the X band frequency range? No, anyone? You know the C band, X band. At least you know the Bluetooth frequency or Wi-Fi frequency. Hello? Are they there or not?
Sir, 8 to 12 gigahertz.
Guys, please respond.
What is the Wi-Fi frequency range? What is the Bluetooth frequency range? Anyone?
Sir, 2.5 gigahertz to 5
Sir,
gigahertz.
2.4 to 5 gigahertz.
2.4 or 2.5 gigahertz. That means if you choose suppose you are choosing, you are designing one antenna, that antenna works at Bluetooth purpose or Wi-Fi purpose. That antenna resonating at particularly 2.4 gigahertz. But here I am designing one antenna that resonating is 12.5. That means, so this is applicable to the X band application. X band means, you know the X band. X band starts at 8 gigahertz to 12 gigahertz. That's why these antenna produce the 3 resonant frequencies. That means one is the 12.6, it is working, and 13.78 is working, and 14.72 working. That means this antenna works within the X band application only. In the X band, it covers the satellite application. That means, so this design, it covers this antenna, whatever the antenna I am designing, this antenna used in the applications of satellite applications. So based on the design, you can choose the application. First of all, you can choose the either Bluetooth or WiMAX or WLAN. Suppose you choose the WLAN application, that is the 5.4 gigahertz. So you can change the dimensions of this patch. That means here I'm choosing the length of the patch and width of the patch. You are increasing the length of the patch or width of the patch. So based on that, you get the some results. So based on that result, that your antenna works for that particular application, that particular frequency. Is it clear? So here I'm changing this one. See here, this is getting the 3 bands. So I am increasing the length of the feed. Is the feed here? This is the feed is there. Here generally in the feed length I'm giving as 1.5. Then I'm changing the feed length is 2. So next week we are designing one microstrip patch antenna for the. How many members are there total? Hello? For class 10th is 100 members or 120 members?
170.
170.
Okay, for the next week I'm showing everything. So similarly you can design different antenna. That means you have changed the different patch length and different width. Based on this, first 30 members you can choose the frequency below 5 gigahertz. Next 30 members, so 5 to 7 gigahertz. Then next 30 members, that means up to 60 members. First 30 understood. First 30 members design the operating frequency below 5 gigahertz. Next 31 to 61 members, 5 to 7 gigahertz. Next 61 to 90 members, 7 to 10. So last, that means 90 to 120 or 170 total numbers. They are all designed the frequency in between 9 to 12 gigahertz. Everyone understood my question? So next week, sir, lab copy is there, Raju sir.
Yes. Yes, Anand
Previous,
sir.
previous they submit the lab copy na.
Yeah,
So
yeah.
like this, these members also submitting lab copy.
They should submit their lab copy. Yeah, but yeah.
Okay.
This is
Okay.
this is their second lab, I think. Na, Anand sir. The first one is
First
introduction of
devices.
component.
Yes.
Devices and components.
Introduction.
Yeah.
So that one is
This
submitted or not, sir?
Yeah, already almost they have submitted. Okay.
Okay, okay.
Now.
So
in
this
this,
is the first introduction, right? That one is introduction or experiment 1?
Experiment one.
Okay.
Okay.
Then this is the listen. This is the experiment 2. That means write down everyone. Name of the experiment is designing of microstrip patch antenna with designing of microstrip patch antenna with microstrip feed line using HFSS. So this is the second experiment. So you choose generally I'm choosing some dimensions, that is the patch length and patch width. you can choose any values, you can design the antenna. So it covers the, so first 30 members it covers below 5 gigahertz, next 30 members covers 5 to 7 gigahertz, next to 7 to 10. So 90 to 180 students covers the 10 to 12 gigahertz frequency range. That means just you can vary the, see, just you can vary the length of the patch. That means length, this is the length or width or feed length you can vary. So you get the results. So now I'm choosing the feed length is 1.5. Right now I'm increasing the feed length is 2. So you can see the result. You are getting one more band is I'm getting. So previous is 3 bands are getting here, 1, 2, 3, 4. So like that you can vary the frequency, we vary the dimensions of the patch. You get the operating frequencies or desired applications. So this is the reflection coefficient. Then how to check the VSWR? So click on the results, that is right click, go to the same first one, create model solution data report, rectangular plot. In the rectangular plot here, VSWR is there. This is the VSWR. So choose here, this is the VSWR, here VSWR1. Here function is the VSWR units are dB. That's why choosing the dB. VSWR, VSWR1 and dB. So generate the new report. So generally here, C1. This is the, what are the VSWR range value? Anyone knows? So VSWR is less than 2 value. So select this one, mark and add mark. This is the 2.7. So that's why, see here, if the VSWR value is not getting below less than 2, your designing is not good. That's why you can change the, go to the design part. So this design part you can change the values. So previous I'm choosing the 1.5. So then right now I'm choosing the 1.5 feed width to 1.2 value. That's why for choosing the 2 value, this is not getting. So you can choose the 1.5, and 1.5 is the better values are getting. Once again, is it simulating? You know, so all parameters, how to verify the radiation pattern gain. Everyone knows. So first one, checking the the far field setup, infinite sphere. Models are free stand. Not assigning the So see here, this is the radiation. To check the gain value and radiation patterns, see here, just click on this radiation. So this is the radiation in the project manager. Last one is the radiation is there. Click that radiation and right click. So click on the insert far field setup and infinite sphere. In the infinite sphere, we are giving the phi value and theta value. That means if we show the field distributions, that means how much fields are radiated into the free space. That is, so this is the 3-dimensional. That's why it is requires the phi value and theta value. So here generally phi value taking as taking the phi value 0 to 360. That is the entire region. So the theta value is minus 180 to 180. So click on the radiation. It shows the infinite sphere. Phi value is 0 to 360. Theta value is minus to 180 to 180. This one. We go for the then once again run. So how to show the S parameter and VSWR is clear. Any more doubts? How to verify the scattering parameters, that is the reflection coefficient S11 and VSWR. So VSWR value is always less than 2. So reflection coefficient S11 is also taking the minus 10 dB level below. That means, so as much as a low value you are showing for the reflection coefficient S11 value. So this run is completed. So VSWR completed and S parameters are completed. Click on the results. So see here previous did not appear in the far field reports. So you did not assign the radiation. Here radiation means, so these values in the infinite sphere, phi value 0 to 360, theta value minus 8 to 180. We did not assign this one. We did not come to the here radiation far field. See here, create far field reports. So in this section shows the gain value and radiation pattern. So here first see the gain, create far field report, go to the, see here radiation pattern. This radiation pattern here, gain total and dB. Gain total dB. Here choose the solution sweep as a sweep. Go to the families. Here we are already previous in the assign in the radiation phi value and theta value. Here phi value here showing whatever the frequencies at values we are required, 0 degrees, 2 degrees, 4 degrees. So if we choosing phi equal to 0 degrees, that is the E plane, phi equal to 90 degrees, phi equal to 90 degrees, that is the H plane. So if we choose the phi value as a 0 degrees, this is the E plane, phi equal to 90 degrees as H plane, and your resonating frequencies are, what are the resonating frequencies? 12 point something, 12.66. So that's why 12.66, I'm choosing them 12.66. Then that one is create far field report, gain total dB. .34. So this is the gain. The maximum gain is getting 6.42. So this is the red is the maximum field is radiated in the desired direction. So this is below is the, these are the green color and blue color. Blue is the less radiation fields. That means your antenna radiates the maximum energy into free space. That means here maximum red shape is there. That's why. So this is the gain value is maximum value is 6.42. Okay. So how can you once again see? How can you see the gain value? So just to click on the result, right click, create the far field report, go to the 3D polar plot. 3D polar plot. Here gain total just to dB. So here solution is the sweep. Go to the families. Then what are the frequency we're showing? So 12.6 or 10. So this is I'm choosing the 12.66 frequency. What are the frequency you can choose? That is the resonating frequency. See here at the 12.6 gigahertz, the gain is 5.36. Previous, the gain is 6 point something at 10 gigahertz, 10 point something. So this is the so compared to here previous one. Previous is maximum red part is there and gain is 6 point something at 10 gigahertz. But here around 12.66 gigahertz, the gain value is decreases. That means at 10.9 gigahertz, your antenna resonates the maximum electromagnetic fields. At 12.6s, it reduces the at 10 gigahertz to 12, the fields are reduced. So these are the gain. Okay, then another one is show the radiation pattern. So go to the create for field report. Go to the see here radiation pattern. In radiation pattern, gain total dB. So select the solution, sweep. Go to the families. Here radiation pattern E plane is there and H plane is there. E plane pattern and H plane pattern. So for the E plane pattern, you shown the select the phi value. Here phi equal to 0 degrees, you produce the E plane. If phi equal to 90 degrees, that is E and H perpendicular to each other. That's why choose the H plane is 90 degrees. But resonating frequency is maximum at 10.94. That's why. So see here, this is the radiation pattern. So radiation pattern, this is the red line. Here red line is so phi equal to 0. This red line is the E plane. So this is the gray color line is phi equal to 90 degrees. This is the H plane. Okay. So for this designing antenna, we are showing the S parameters, VSWR, gain plot, and radiation pattern. Any more doubts in this? How to check the reflection coefficient S parameter, how to check the VSWR, gain and gain plot? No doubts now still now? So in this experiment, so this is the designing of microstrip patch antenna using microstrip field line with HFSS. Microstrip field line, you find the S parameters, VSWR plot, gain and radiation pattern. So these are the 4 parameters. And the 4 parameters showing in the microstrip patch. So any more doubts? For the next lab, you can submit this lab copy. That means along with you choose the dimensions. I am not giving the dimensions. So I am choosing this. See, once again, check the dimensions. So highlighting what is the radiation surface. So this is the substrate dimensions. Note down the substrate dimensions. So this is the substrate position minus 8.617.390. So this is the substrate length 17.22, width is minus 14, not the minus here. I'm choosing the positive value. That means here this is the origin, center is the origin. So this is the length, this is the width. So this is the length is 17.2, width is 14.78, and height 1.6 is the height of the substrate. So this is the substrate dimensions. Then we are designing the patch. So go for the patch. This is the patch dimensions are. So patch length. Patch length is 7.62. This is the 7.62 patch length. So this is the width is this is the width. Width is 7.62. Length is 5.18. This is the patch dimensions. So similarly, not taking these values, you can choose any values, okay, and modifying the corresponding values. That means suppose I'm choosing the what are the values I'm choosing? 7.62, choosing 5.18. You can choose 9 or 10 or 11. So if you increasing the, see here, if you increasing the patch dimensions, what happens the result? If you decrease the patch results, what happens the result? That means the result is resonating frequencies are increasing or decreasing. You can observe based on the change the dimensions of the patch. So this is the patch, this is the feed. So this is the feed dimensions. That is the feed is I'm choosing feed width. So feed width is, this is the feed width 1.5. This is the feed length. Feed length is 3 approximately. So this is the excitation port. This is the excitation port. Then so this is the ground. So this is the red one is the ground. So simply here design the first whatever the antenna you can choose, design that one. Then so this is the here designing settings, 3D model, boundaries and excitations. Boundaries and excitation means excitations is the input signal. Boundaries means you give the perfect electric field to the patch and as well as ground. Then mesh operations. Mesh operations means go to the analysis and set the frequency, optimizing frequency. So then optometrics means, okay, previous you know the optometrics, anyone knows how to use the optometric values? Hello, please respond fast.
No, sir.
You know the optometrics or not? Okay, later next you can remind me on next lab. I will explain the how to choose the optometrics. Okay, then finally this is the radiation maps. So anyone is doubts are there regarding in this design? Just I'm showing the 4 parameters: S parameters, VSWR plot, gain plot, and the radiation patterns. So in the next lab, all the members design the any rectangular shape or patch shape, any shape that is the radiating patch corresponding. You can choose the dimensions. Okay, you can choose randomly, not in the particular, but you get the result. That based on the result, you can suppose for this one, what is the value here? See for this. So see here, I'm getting around some modifications are done. That's why finally getting 10.92. So 10.92, I'm getting minus 15. Okay, you can change the patch length and width and feed. Every parameter you can change the frequency. That means the result is moving upwards or moving downwards. So that one you can observe. That means generally if you choose the 2.4 gigahertz, that is 2.4 gigahertz means we design the one antenna for the Bluetooth applications and Wi-Fi applications. So WLAN means LAN connection is around 5.2 gigahertz and 5.4 gigahertz. Like that, if you design your antenna working at works at satellite applications, that is in between 8 to 12 gigahertz. What are the 5G frequency ranges? Hello? Anyone knows about the 5G frequencies? In the upcoming years, the 5G is coming now. So what is the 5G frequency ranges? Anyone?
Sir, up to 100 gigahertz.
Oh, up to 100. No. Okay, that is approximately 26 or 28 gigahertz.
So more than 24.
Nowadays, we are using the frequency. Yes. So, how to get the, suppose my question is, you are getting, suppose I'm getting for this 10 point line, around approximately 11 gigahertz I'm getting. So suppose if you increasing this frequency to 5G band of, that means 5G applications. So that means suppose your required frequency is approximately 25 gigahertz. What you changes in this design? Anyone saying? Or understood my question or not? So in the nowadays wireless communications, that means your mobiles also accepting the 5G. So previous is the 4G mobiles are there, nowadays 5G mobiles are there. That means for the 5G mobiles accepting the 5G frequencies. That means if you require the 5G is approximately, suppose I am taking the 25 gigahertz. So my resonating frequency is getting around at 25 gigahertz. What we are doing the changes in this design. Anyone?
Sir, we need to increase the length of the patch.
Communication student. Yeah, you can change the, listen, you can change the length and patch. So that means if you get the frequencies high value, your length and patch is the less value. That means if you decrease the patch length and width, your frequency is increases. See here, suppose what the, so see, my patch length is 7.62 mm. Here this is the units are mm. If you choose these 7.62 in millimeters to micrometers, you are automatically getting the frequency is high. Then your frequency, resonant frequency is high. That means you can design a antenna for the 5G applications also. Is it clear? That means nowadays, if the decreasing the antenna size dimensions, you are getting the high frequency applications. Is it clear? So that's why you are using the previous 4G mobiles, your antenna is very small antenna is using. But in the 5G applications, in the mobile technology, the 5G application frequency is high. That's why antenna is very less. If the antenna is very less, means automatically it increases the radiation effects. That is the radiation fields. Okay, is it clear? Okay, that is the theoretical concept. We don't know your analysis and already studied the theoretical concepts. So here today we will learn the experiment is a design of microstrip patch antenna using a feed line with HFSS software. So design the antenna. So find out the 4 parameters. Listen, S parameter, VSWR parameter, gain plot, and radiation patterns. Radiation patterns is both E plane and H plane. Is it clear? Any more doubts is there? So within 5 to 10 minutes, I will close the lab session. Any more doubts? Quickly ask, fast.
Sir,
Sir is taking attendance. Raju sir. Hello. Some students are now also ask the questions. What's the doubt?
Sir, in case of 5G, if we are using smaller antennas with high frequency, and if the field is very strong radiation field, then it might have some health issues with the mobile radiation that comes in. Or is it just like it doesn't happen?
That's why I'm saying lifetime is reduces if the radiation effect is high. If the radiation effect is high means what is that means? Radiation effect is high means automatically field distributions is high. I'm showing here. Suppose see here. What is this? Here this is the radiation now. This is red color is the radiation. That means if a high radiations is getting, that means if your body is suppose every day using the high temperature, what happens?
Yes, sir. It damages.
What happens to your body? That's the problem. Okay,
Sir,
that's why the technology increases.
Sir, the thing is that before the upcoming means in 1G, 2G, that time it was slow. But when we got 4G, it was quite fast.
Yes,
so
yes.
why do we need 5G? 5G for?
Right now we are using the 4G plus. If you on the mobile data, some of the mobiles showing 4G plus. You can observe that. Mobile data symbol na 4G plus and LTE symbol also there.
Yes.
LTE means long term evolution. So this is nowadays we are using the 4G plus. So in this year the government is maybe launching in the 5G. That means that frequencies shifted that almost double. Right now we are using the how much frequencies? Wi-Fi, WLAN, all of the less than 10 gigahertz. Na?
Yes, sir.
So if you go for the 5G technology, that means the frequency is around 24, 25, 26. That means 20 above.
Yes, sir. That means our life expectancy will reduce to half.
Okay, yes. So here the concept of in the designing of antennas means first you can choose your application. Either so I am choosing what application means that is 5G application is choosing your resonant frequencies beyond the 20 gigahertz above. If the 20 gigahertz above means you are reducing the patch dimensions. Patch dimensions, suppose now I am using the millimeters. You can convert it to go to the millimeter to micro. Or you are increasing the frequencies, less frequency. That's why you are increasing the patch dimensions is high. That is inversely proportional. Okay.
Yes, sir.
So you are calculating the S parameters, VSWR, gain and radiation patterns for these. So next week I will show the another technique. This is the microstrip feeding. Then you read already coaxial cable and coplanar CPW, coplanar waveguide feed. Or 4 or 5 methods are there. 5 techniques already studied in our antenna subject. So in this lab, I am discussing 2 or 3 feeding techniques. Then, so already that's why I already studied in the antenna subject and antenna lab also. I am just to rewind these 1 or 2 experiments. Then go for the microwave circuits, microwave devices. So that's why you already sir told to me the fundamentals explained previous labs. What are the devices, radiation coupler, microwave bench setup. They did know everything. Hello? Okay, sir is taking attendance or not? Okay, please leave.